All right, our last talk for the day. My name is Ben Schmerler. I just did the talk a little bit ago about toilet hacking. I work with ISC. You can want to talk to me more, I'm over there. But today, or this last session, I'm introducing Lenin Alevsky at Google and Max von Blankenberg, who are going to talk about some security stuff. So please welcome to the stage.
Hello everybody. Thank you so much for coming. My name is Lenin Alevsky. I'm a security engineer at Google. I'm also a volunteer at Pacific Hacker Association.
And I'm Max von Blankenberg. I'm a security researcher at SemGrep and another volunteer at Pacific Hackers.
So before we start, the usual disclaimer, the opinions expressed here are not the opinions of our employers or the organization. So with all that said, this is the agenda for today. We're going to start with a quick introduction on what are containers and containers technologies, what the hell is Kubernetes, the Kubernetes threat model. Then we are going to talk about the most common attack techniques, some built-in defenses, and finally the Kubernetes evolution. So probably if you are here, you are concerned about process isolation, right? Application compartmentalization. So at the beginning, this was a simple problem to solve, right? In the traditional architecture, it's as straightforward as putting one process per machine. But what this is a straightforward solution, this is not cost effective. Then we have the virtual machine architecture, where we have a special component, which is called the hypervisor, which is capable of virtualizing an entire operating system, offering some degree of isolation. However, this still is a problem because virtual machines tend to be big and you cannot move them. Finally, we reach out the container architecture, where we have a component called the container runtime that is capable of running what is called a container. A container is a special format for your application that is packaged with its source code, configuration, and dependencies, and it's able to run as if it's running in its own separated hardware. While this is cost-effective and performance improved, it's not a silver bullet, and we're going to explain why. So I mentioned the word container a couple of times already. But what if I tell you there is no container? In reality, it's just another process running on your machine. So yeah, what containers really are. So in reality, containers are a very clever operating system virtualization that use some of the features of the kernel to offer some degree of isolation. Those features will be namespaces, which basically control what a process can see. C groups, short for control groups. They are very useful to assign different resources in terms of network throughput, CPU, memory, and finally capabilities, which control the level of privilege a process can have in your system. Next, Max is going to talk more about what is Kubernetes.
Thanks, Lenin. So we talked a little bit about what containers are. Now let's explain what Kubernetes is. You can probably think of Kubernetes, if Docker is a shipping container, then Kubernetes would be the fleet of cargo ships running them. It's an orchestration tool, a framework for building distributed systems, an alternative way that you can deploy your applications. In general, it can be called the operating system of the internet. As many containers as you want at lightning speed. In this talk, there's going to be a lot of terms we're going to throw around, so I'm going to define some of them real quick. First and foremost, services in Kubernetes refer to the way Kubernetes allows users to access your applications. These are the public IP address and port. A pod is a group of containers that are deployed together. These share network namespace and can also share file system namespace. A node refers to the virtual machine that's used to run containers and pods themselves. And a node cluster is what forms the backbone of a Kubernetes application in general. Containers are grouped into pods, which are allocated and run on nodes inside of a Kubernetes cluster. And finally, we have a deployment, which is the set of configuration values that define a cluster, describes how your pods are allocated and managed. Breaking it down a little bit further, this is kind of what a Kubernetes application looks under the hood. On the front, you have plain service, which is all your user sees. But behind that service is any number of nodes running any number of pods, running any number of containers each. Breaking it a little down further, we'll get into the Kubernetes components. There are control plane components, which are unique to a cluster. These include the kube API server, which is the main control plane for the Kubernetes cluster. There's etcd, which is used for data storage, config maps, secrets, etc. The kube scheduler, which schedules newly created pods to be run on nodes. And the kube controller, which monitors and manages those pods to make sure they're running correctly according to your deployment. And unique to every single node is node components. These include the kube proxy, which is the interface between the node and the kube API server. The kubelet, which is the control agent for a node. It communicates with the API server. And, oh, I'm sorry, I'm incorrect. Kube proxy proxies network traffic between the node and the service. The kubelet is what interfaces with the kube API server and controls your node. And finally, there's a container runtime like Docker, which runs containers on the node. With this model of Kubernetes, we also have a threat model, of course. If an attacker can control a container or a pod, they control the application, and they may be able to escape and attack the node. If they control the kubelet on a node, they control all the pods running on said node. If they control the worker nodes, they control all the pods running on said node and can also escalate privileges to attack the master nodes. And if they gain access to the master or the control plane nodes, they control the entire cluster. They can add, modify, and delete everything. So with new threat models come new risks and new OWASP lists. Here's the Kubernetes OWASP top 10 list, and moving forward, Lennon will tell us about the Kubernetes most common attack techniques.
Thank you, Max. So Kubernetes common attack techniques. In 2020, researchers of Microsoft put together a threat matrix like the MITRE attack that consolidates all the different tactics and procedures that affect container environments. So this matrix is very similar to your traditional Linux systems, but at the same time it's different. For example, initial access to the machine becomes initial access to the cluster. Or running malicious code on the machine becomes running malicious code on the cluster or the container. 1 year after that, the Microsoft researchers update this matrix, and also with the help of independent researchers, they add additional tactics and techniques and procedures they observe on the wild, and they also remove some others that they were not relevant anymore. So in this talk, we're gonna mention into each one of those. So initial access. The initial access phase will be all the tactics and techniques that attackers and adversaries will use to put one foot in the cluster. These may include things like using cloud credentials, compromised registries, the kubeconfig file, and so on. For example, when it comes to using cloud credentials, attacker may prefer to use traditional phishing techniques to steal access to your favorite cloud providers that allow them to get access to a UI, a management UI, to a console to control a Kubernetes cluster instead of attacking directly the cluster. So this is still effective, and even in a scenario when providers offer multi-factor authentication, they are able to trick them with techniques like MFA bombing and so on. Next in the list is sometimes an attacker will prefer to compromise container registries. So container registries will contain a list of images, and if an attacker is able to push there a malicious image or a malicious dependency, so raise the hand who here has to deal with the XX vulnerability. So this is a good example of supply chain attacks in which containers didn't directly attack the cluster, but they were able to backdoor one of the dependencies, which end running inside an image in the cluster. So the next in list will be hunting for kubeconfig files. So the kubeconfig file is very important because it contains the credentials to connect to a cluster. So in this example, I did a very simple GitHub search. And you can see by searching for this simple term, you are able to get credentials. And you may try to use these credentials to connect to a cluster randomly on the internet. So this works particularly well for attackers if they get their hands on some developer's machine, and then they will have basically the same level of privilege that the developer will have. Next in the list, we have application vulnerabilities. So at the end of the day, we are running web applications in our clusters. So if those web applications are vulnerable to common vulnerabilities like remote code execution or SQL injection, that will be an entry point into our clusters. These vulnerabilities are commonly covered by OWASP Top 10 and many other documentation. And finally, we have exposed sensitive interface. This one is very, it's funny for me because at the beginning, by default, the Kube API server came with its own UI, and that UI was commonly exposed to the internet. At some point, Kubernetes developers fixed that, but several projects now they include their own management UIs, and sometimes they are exposing to the internet with default credentials or not any protection at all. So if an attacker is able to find one of these, that's an entry point to the cluster. So next, Max is going to talk about the execution phase.
Thanks, Lennon. So moving forward to execution, we have many techniques used by attackers to run their code inside of a cluster. It allows an attacker to gain a foothold for further exploitation. OK, yeah. So first on the list is the application exploit. And Lennon mentioned that a little bit. If there's a vulnerable application running in a container, that can be exploited to gain access to the container and run your code inside of it. And the other three are more unique to Kubernetes. I'll explain them in a little more. That's back, my bad. Yes. Attackers can run exec inside containers. If an attacker gains access to account credentials and they can access the Kubernetes API server, they can run kubectl exec and exec their code on a running container. That's one example. But in some cases, attackers can't exec into specific containers. For example, if it's a Scratch container. In these cases, attackers can simply run their own containers on the cluster and deploy them from Scratch. This is a common way that crypto miners are deployed in clusters. And if an attacker wants to be especially sneaky, they can deploy a sidecar container inside an existing pod. Usually pods have one main container that they have running, but they can have any number of sidecar containers as well. So putting another container inside an existing pod can hide it from monitoring tools and the like. After execution, we have persistence. I believe you're covering. No, I'm covering that. Excuse me. Yes. In persistence, we have tactics used to maintain the initial foothold held by the attacker after exploitation. Let me see. We've got a basic backdoor container. As mentioned before, attackers can deploy their own containers to execute code in the cluster. This can be used to maintain persistence because it's a backdoor, and it will keep running. You can also use Kubernetes cron job. Kubernetes job is a specific implementation in Kubernetes that allows specific containers that are meant to run specific jobs to run at specific times. It's like cron job on a Linux machine or any other machine. So it spins up you can spin up a malicious container at any time to run a job, and then it spins down. Harder to detect. Some more obscure techniques include a writable host path mount. If an attacker is able to create a new container, they may be able to create it with a writable host path mount as well. This means that the container has write access to the host, the node that's running the container. And this, as you can imagine, is very bad because then the attacker can write whatever they want on the host. They can write to the authorized key file and add their own SSH key. They can add a cron job, etc. Finally, we have the malicious admission controller. The admission controller is a Kubernetes tool that looks at deployments coming into the cluster and reads and optionally modifies them. It's an audit tool. If an attacker takes this over, they can leverage it to inject a malicious container into a valid workload. Here we have a legitimate user. The attacker adds their container to the workload, and Kubernetes deploys it as if it's a legitimate container. Now, Lennon will talk about privilege escalation.
Thank you, Max. So moving on, privilege escalation techniques will be all the tactics and techniques really the adversary will do to move forward in their attack chain. For example, if they compromise a regular application, they will try to break out into the host system, right? If they are already at the host system, they will try to move to different nodes. If they are moved to different nodes, they will try to compromise a control plane. They can do this by many different ways. Max already talked about hostpath mounts. Another way is compromising additional cloud resources. For example, let's say an attacker compromised a container and that had access to a cloud bucket like S3, or even a credential for an identity provider, so on. But let's take a second to appreciate these 280 character tweets that will compromise your Kubernetes cluster. You can take a picture. You may want to try to run this in your cluster and see what happens. But really, what this command is doing is creating what is called a privileged container. So a privileged container, in reality, is a process that has access to all the host PID namespace, process namespace, has access to all the network namespace of the machine. So it can see everything that is connected to the sockets, and it has access to all the files in the system. A malicious attacker can do that with that simple command. So in this example, they achieve that by getting some cluster credentials or compromising a Kubernetes management console. They deploy that on a particular machine, and then it's equivalent of they controlling the whole machine. But sometimes privileged containers are already running in the cluster. This is the case for a very old privilege that used to exist in Kubernetes by default, calling named the cluster admin role. So the cluster admin role will be the equivalent of a super user on a traditional Linux system. So if an attacker is able to compromise a container that has this token inside, has this particular role assigned, it may be trying to escalate privilege to deploy additional malicious workloads, such as crypto miners, or really reading every secret from the etcd NoSQL store. So moving on, Max is going to talk more about defense evasions.
Thank you. So defense evasion consists of tactics used by attackers to avoid detection and hide their activity. Basic. So one of the first techniques here is clearing container logs. This is just the application running at the container is generating application logs. You can clear these. You can clear the Nginx logs, etc. There's also Kubernetes events. Kubernetes events track any changes that happen in the cluster inside Kubernetes. These can be deleted using kubectl delete events all to hide their cluster activity. They can also use something similar to typo squatting, naming their malicious pods or containers similar to valid pods. This makes it easier to hide malicious pods, and maintainers might not recognize that their cluster has been compromised this way. There's also connecting from a proxy server, which is connecting from a VPN, or if an attacker leverages access inside the Kubernetes network, they can deploy their attacks from inside the network. The call is coming from within the house type of thing. Basic Yeah, you get the idea. Moving on to credential access, there are a lot of credentials that can be found in Kubernetes clusters. This consists of techniques used by attackers to obtain these credentials. They can, of course, list Kubernetes secrets with a simple Kubernetes command. Kubernetes has built-in secrets. There's service principal credentials, which are cloud credentials. These can usually, attackers can usually leverage their access to containers to access service principal credentials. In this case, they actually usually have to access a node. Moving forward, there's container service account credentials. By default, service accounts are created for every pod in cluster. So an attacker, if an attacker is able to steal the credentials for that service account, they're able to perform actions on the pod. There's a very common one, application credentials in configuration files. These are, in your deployments, credentials. If you don't deploy your credentials in secrets, you may put them directly into the deployment configuration files. This is a very bad idea. We have some mitigations for that later in the talk. Please don't do this if you have the ability to. It makes it very easy to steal. There's also managed identity credentials, which are another form of cloud credentials. These can usually be queried if an attacker takes over a container. They can query it and use it to gain information about cloud resources, such as the underlying node. And finally, the admission controller, if taken over, can be used to read deployments, deployed workloads. And these can have sensitive information in them as well. Moving forward, the discovery technique allows attackers to enumerate their environments, perform lateral movements. And there's many ways they can do this, of course. They can access the Kubernetes API server, which controls the entire cluster, so you can gain information about the whole cluster this way. And if they don't have access to the Kubernetes API server, they can access the kubelet API. The kubelet API is, by default, or the kubelet itself by default exposes a read-only API that does not require authentication, which is usually a lot easier to access than the Kubernetes API server. This can be used to read information about, I believe, the running pods and the node itself. They can also map the Kubernetes network as usual using tools like NPM. By default, containers and pods don't have any restriction on on who can communicate. Pods have, sorry. By default, pods have no restriction on which pods can communicate with which. So if an attacker controls one container, they can query the whole cluster, map the whole network, unless you put in network policies, which we'll get into later. They can also access the Kubernetes dashboard to view information in the web UI. And they may be able to access an instance metadata API. This is a cloud API. Attackers that gain access to a container may be able to query this API in order to gain information about the underlying node, which is dangerous, of course. Moving forward, Lennon, can you tell us about lateral movement?
Yeah, we have a lot more content to cover, so I'm going to move fast. So yeah, lateral movement. These will be tactics and techniques that attacker will use to traverse or cluster or traverse different environments, like multi-cloud environments, different machines, different privileged pods. So to do that, the attacker may leverage access to cloud resources, as I mentioned. Let's say an attacker compromises a container. There is some privileged credentials to access some cloud resource on a cloud. They may try to steal container service account. So service accounts in Kubernetes is the main way they assign identities to the different workloads. So in case they compromise a privileged identity, they can use that to pretty much impersonate the workload and the cluster. Max already mentioned the lack of network segmentation. So an attacker may try to use regular networking tools like Nmap to scan the whole cluster. Containers may include application credentials in configuration files, such as service account, tokens, database credentials, and so on. They may also try to exploit writable volume mounts on the host. And finally, they may try to do core DNS poisoning, which core DNS in Kubernetes is one of the main mechanisms they do DNS resolution. So if an attacker is able to compromise core DNS, it can impersonate the process. So moving on, we have collection, which I already mentioned a little bit at the beginning. So sometimes for attackers, it's easier to try to target Docker registries or container registries. But sometimes if they are already in the cluster, let's say your organization has its own private registry, to access that private registry and pull credentials, you need some type of put containers, you need some type of credentials. Attacker can steal that, and then they can pull any container image they may want, and sometimes container images may contain credentials inside, right? So that's another way they can do to achieve collection. And finally, let's talk about the impact. So the impact is very simple. It may be data destruction. It may be as easy as removing persistent volumes that doesn't have like a lock to don't be removed. They can also delete logs or events. So in case of an investigation, you cannot, it's difficult, the effort. They may do resource hijacking by deploying their own crypto miners, their own torrent server, or basically abusing CPU and memory resources of your clusters. And they may cause a denial of service by deleting pods, deployments, stateful sets, services, and ingress controllers. So I think that's enough of bad things. So Max?
All right, let's talk about some good things. So what do we do about all this? Oh, wrong button. Yes, there's many different mitigations you can put in place to deal with these attack techniques. First and foremost, we're going to talk about some container restrictions you can put in place to harden your containers. This is a very basic one, resource quotas and limits. You can limit the amount of resources each container is allowed to use. The most common is limits on CPU and memory, etc. In Kubernetes, the resource request configuration tells the kubelet how many resources to reserve for a given container, and the resource limit says this container is not allowed to use any more than the given resource. It's the lower limit and the upper limit. The kubelet is in charge of enforcing these values. It's a very simple way to prevent crypto miners. That's that. There's also security contexts that you can implement in pods, and these go into lots of detail. There's many security contexts. I'll just mention a few. Privilege and access control. Allow privilege escalation defines whether processes in a given container can gain more privileges than their parent process. Privileged defines whether this is a privileged container or not. Alevsky mentioned that a little earlier. Privileged containers are equivalent to root processes on the host. Run as not root, run as user, run as group, control what users the processes run as. There's capabilities management. If you don't want to give full root privileges to a specific container, you can give them specific capabilities of root, but not the entirety of it. These can be configured in security context. You can set file system and mount settings, such as setting file system to be read-only. You typically want to do this by default unless you're writing to the system. And you can set security profiles like security enhanced Linux, seccomp, etc. Moving on past the container, you can set up network policies. And these are very powerful. We mentioned that pods by default have no restriction on the traffic allowed to communicate between each other. Network policies allow you to restrict that. They control who can talk to who. These are implemented by the network plugin or the CNI. To use these, the CNI needs to support network policies. KubeNet is the default CNI, but some other popular ones are Flannel, Calico, Cilio, and Istio. Choose whichever works for you. Now, these are really cool. Pods are not isolated by default, but once there's a network policy in place in a namespace selecting a particular pod, that pod will reject connections from everywhere that don't abide by the network policy. In this example here, we have a network policy that is selecting all pods with the role DB. And in this, we can enforce both ingress traffic and egress traffic. We have a policy that only accepts traffic from the namespace, I believe the project, my project, is what it's doing here. Namespace selector for project, my project. It only accepts traffic from my project. It only accepts traffic from pods with the role front end up at the top here. And it also only accepts traffic from pods that have the IP address in that specific IP range. I won't spell that out for you for sake of time. And you can also enforce egress. This pod is only allowed to communicate to IP address blocks 10.0.0.0/24. Moving on from network, we get to encryption. There's two things you need to look out for: encryption in transit and encryption at rest. By default, network traffic in Kubernetes is not encrypted, but you can very easily encrypt it by setting up TLS certificates. That's it. The API to do this is certificates.k8.io. You can query this to create your own certificates, or you can use a external certificate manager such as certmanager.io. Some network CNI plugins also support this by default. Use whatever works for you. And for encryption at rest, you can use encryption configuration. This enables at-rest encryption for secrets, config maps, any sort of data in your Kubernetes cluster. It supports AES-CBC, AES-GCM. It's somewhat limited, but you can also implement an external key management system, which is much more secure and works on the exact same thing. Quick note is that you cannot use this to encrypt file systems. To do that, you need a different solution, either encrypting the data with your own application or using a storage integration that provides encrypted volumes. Now, Lennon, could you tell us about pod security policies?
Thank you, Max. So now let's talk about access control. So when it comes to access control and follow the principle of less privilege, Kubernetes has several options. So the old one, this is deprecated, but I'm going to talk about because I still see a lot of old clusters that use this version. It's called pod security policies. So at a very high level, pod security policies allow you to define certain rules that you have the roles and role bindings on the left, and they are namespace scope. They will allow you to define a certain level of privilege and access to resources that a particular identity may have in your cluster. On the right side, you have cluster role and cluster role binding, which are exactly the same, but they are not scoped to a particular namespace. So let's say you want to protect your cluster from the example of the privileged pod or the privileged container. The first thing you have to do will be create a pod security policy. In this case, it's a restrictive policy because it will enforce certain configuration that is going to be secure by default, such as host PID equal false, network equal false, and so on. Then you have to create a cluster role. So this will be a policy that will affect the whole cluster. With the cluster role, you will mention your pod security policy, and it's very important. You will say verb equal use, and then finally you use a cluster role binding, which is going to put everything together: the identity or the group or the service account and your policy. So if you want to visualize that, it will look a little bit like a tree structure, in which the cluster role binding is at the top. Then you have your cluster role that is associated with the policy. And on the other side, you have your identity or your group or your user. So the next time somebody tries to deploy a privileged container into your cluster, first of all, it's going to get an error. And Kubernetes is going to prevent that workload to run. So this is a cool way to do it. But a most modern approach will be a pod security admission. So a pod security admission is a feature in Kubernetes that helps you ensure your pod met certain security guidelines before they are allowed to run. Think of it as a security checkpoint that a pod has to pass through. Imagine a gatekeeper for your Kubernetes cluster, and before any request, for example, creating a pod or a service or really any other resource in the cluster, is fully processed, it has to go through a gatekeeper or a checkpoint. The admission controller are that checkpoint, and by itself, it's gonna allow you to prevent malicious deployments or really prevent any misconfiguration that you won't like in your cluster. So here are a couple of examples, like OPA Gatekeeper, Caverno, JS Policy. Each one of that has advantages and disadvantages, so really use whatever works for you. Next, moving on, we have audit log. So by default, Kubernetes has an audit log mechanism, which is very flexible. So once you enable it, it's gonna start logging every operation in the cluster. You can tune it and configure to meet your standards, such as only log particular operations, like creating pods, creating services, creating stateful sets. You can decide if you want to write these logs into your file system or send it to like a SIEM solution or like any other third-party log analyzer. But there is a catch, right? There is a thing that you have to consider, like enable audit log will consume additional resources in your cluster, because for every new request into the Kube API server, there has to be some processing that will consume CPU and memory. Next, finally, we have hardening the Kubernetes component itself. So for doing that, you have several options. One option is to isolate your Kubernetes nodes, which basically means don't expose them directly into the internet. Instead, use an ingress controller and try to separate node traffic. For example, if your machine supports different network interfaces, you can have one network interface for public traffic, like HTTP connection to your own applications, while you have a separate network interface that handles inter-node communication or really use management communication to your API cluster. Next in the list will be protect your kubelet process. Max already talked about that, but really is disable anonymous authentication and instead enable MTLS authentication for the API. Another thing you can do is enable TLS for etcd, which is the NoSQL key store that is gonna handle all the config maps and secrets for your cluster. So you can put a firewall in front, you can enable encryption at rest, you can use a KMS to encrypt the data. And finally, you can use third-party authentication for your API server. So this means putting in front OIDC, OpenIDC Connect, or really building your own custom proxy for authentication. So what's next? So we are still facing many security challenges when it comes to defending Kubernetes. It's become increasingly popular to deploy Kubernetes at the edge for use cases like hybrid environments, IoT, and edge computing. However, we have tools like KubeEdge, SuperEdge, K3s, MicroKAS, and Minikube that have a very low CPU and memory footprint and make it very easy to deploy Kubernetes in low energy devices. But all of that comes with a cost, right? If you remember the threat model from Kubernetes, that make it a little bit easier for attackers. So here are 10 things that you have to think before deploying a Kubernetes cluster next time. So Max?
Yeah. First things first, don't deploy images from untrusted sources in your cluster. Regularly scan your images for vulnerabilities. ASIC, have a good source. Second, don't store sensitive data in Kubernetes secrets. Instead, use an external key management system or use encryption configuration. Third, encrypt your data in transit. Generate TLS certificates for your workloads using certificates.k8s.io, or use a third-party solution like certmanager.io. Fourth, enforce security context and limit resource consumption for your workloads. Prevent those crypto miners, please. Fifth, implement network security policies in network segmentation. Choose a CNI plugin that supports network policies to limit communication between your services and monitor network traffic.
Next, access control. Remember to always enable access control. If your cluster is an old cluster, you have pod security policies. If not, use a pod security admission. And always follow the principle of less privilege. Don't use cluster admin role, of course. Next, turn on audit logging, monitor for unusual traffic or unwanted API calls. Keep Kubernetes version up to date, patch regularly. Hardening the control plane components and lock down the kubelet process, very important. And finally, adopt a GitOps practice methodology for managing your cluster. That will allow you to enhance security, auditability, consistency, and really it's going to prevent a single user to make unilateral changes into your cluster because it has to go through a revision process. So that reduces the impact. So with that said, thank you so much for attending this talk. I think we have some time for questions, if people want to ask some questions.
Yeah.
So there is a mic in the front.
Quick question for you, gentlemen. By the way, brilliant call. Do you know of any kind of tools, any of the AST tools would check for all of those vulnerabilities you spoke to and make recommendations?
AST tools like Snyk, yeah. So I'm personally familiar with Socket. I know that they do container scanning. I believe Deepfactor also does container scanning. Socket is more supply chain vulnerabilities, and Deepfactor is, I think Deepfactor is supply chain as well. That's all what I'm familiar with.
Yeah, there is a bunch of popular tools that I have used in the past for doing like cloud audits. One of that will be KubeBench. It's gonna check against a list of NIST, like a checklist of like your cluster. It's certified and has all these security controls in place. There is another very popular called NetScout, I believe, that will allow you to do really like cloud security audit, but it has a component to do specifically Kubernetes, and it supports pretty much all the clouds. So those are the ones that I have experience on. Oh. Yeah, any other question, Jeroen? No? If not, we are going to be hanging out at the Dark Arts Village. We are there with the Pacific Hacker Association. If you want to come, we're going to be there talking. And have a good one. Thank you so much for attending.
Thanks for coming, everyone.